Have you ever noticed that a door is easier to open when you push near the doorknob instead of near the hinge? The force may be the same, but the turning effect is very different. That turning effect is called torque. In this video, we will introduce torque and connect it to rotational motion. We will see that torque depends on three things: how large the force is, how far from the pivot the force is applied, and the direction of the force. By the end, you should be able to look at a force on a door or a rigid object and predict whether it produces a large torque, a small torque, or no torque at all. Before defining torque, let us place it in the broader idea of equilibrium and statics. For an object that is stationary or moving with constant velocity, the net external force is zero. Forces may still be acting, but they are balanced. We say the object is in equilibrium. Statics is the study of forces in equilibrium. Up to now, equilibrium often meant no acceleration in a straight line. But rigid objects can also rotate, so we need another condition. The object should not have rotational acceleration either. This is where torque becomes important. A force can be balanced in translational sense but still tends to rotate an object if it is applied away from the axis of rotation. So in this part, we begin extending Newton's laws from straight line motion into rotational situations. Now let us define torque and look at what controls the turning effect of a force. Torque is the tendency of a force to rotate an object about an axis or pivot point. In the door example, the hinge is the axis of rotation. A force applied near the doorknob can rotate the door much more effectively than the same force applied close to the hinge. The amount of torque depends on where the force is applied, how large the force is, and the direction of the force relative to the door. So, torque is not just about force, it is about force applied at the right location and in the right direction. A force that tends to rotate the door counterclockwise produces counterclockwise torque. A smaller force at the same distance produces a smaller torque. The same force applied closer to the hinge also produces a smaller torque because the lever arm is shorter. If the force acts in the opposite direction, the door tends to rotate clockwise instead. So torque has direction, clockwise or counterclockwise. The slide also shows that a force is most effective when it is perpendicular to the line from the pivot to the point where the force is applied. If the force is angled, only the perpendicular part of the force contributes to the rotation. If the force pulls directly along the line through the hinge, the torque is zero. The force may be large, but it does not make the door rotate because the line of action passes through the pivot. Now we can write the torque calculation in a compact form. The magnitude of torque is calculated using the distance from the pivot, the force, and the angle between them. Torque equals the distance from the pivot to the point where the force is applied multiplied by the force multiplied by the sine of the angle between that distance direction and the force direction. The distance from the pivot is often called the lever arm distance. The force is the magnitude of the applied force. The angle tells us how effectively the force produces rotation. If the force is perpendicular to the lever arm, the angle is 90 degrees. The sine of 90 degrees is 1. So the torque is as large as possible for that force and distance. If the force points along the lever arm, the angle is 0. The sign of 0 is 0, so the torque is 0. That means no rotational effect about that pivot. There is another equivalent way to think about this, using the perpendicular lever arm. The symbol for torque is the Greek letter tau. In this equation, the distance is measured from the pivot point to the point where the force is applied. The force is the magnitude of the applied force, and the angle is the angle between the distance direction and the force direction. A very useful idea is the perpendicular lever arm. Instead of thinking about the full distance and the angle separately, we can think about the shortest perpendicular distance from the pivot to the line of action of the force. Using that idea, torque equals the perpendicular lever arm multiplied by the force. These two ways of calculating torque are equivalent. You can use distance times force times sine of the angle or perpendicular lever arm times force. The best choice depends on what the diagram gives you. The physical meaning is the same. Torque gets larger when the force is larger or when the force acts more effectively farther from the pivot. Now let us define the sign convention and unit for torque. Torque has a sign that tells us the direction of the rotation it tends to produce. In this course, counterclockwise torque is taken as positive and clockwise torque is taken as negative. This sign convention is similar to choosing positive and negative direction in linear motion. The sign does not tell us whether torque is good or bad, it tells us rotational direction relative to the chosen convention. The SI unit of torque is Newton meter. That comes from multiplying force measured in newtons by distance measured in meters. Even though Newton meters has the same base units as joule, torque should be reported as Newton meter, not joule, because torque describes rotational tendency, not energy. Now we can solve a short torque example using a door and a string. The string is tied to a doorknob 0.72 meters from the hinge. At the instant shown, the force applied to the string is 5 newtons. We need to find the magnitude of the torque on the door. The hinge is the pivot point. The distance from the hinge to the doorknob is the lever arm distance. The force is applied along the string, and the angle between the door and the force direction is 57 degrees. Because the problem asks for magnitude, we only need the size of the torque, not whether it is clockwise or counterclockwise. However, it is still useful to think about the direction. The force tends to rotate the door about the hinge. Before calculating, let us predict the size. The force is small, only 5 newtons, and the lever arm is less than 1 meter, so the torque should be only a few newton meters. Now let us substitute the distance, force and angle into the torque relationship. Let's first write down the given values. The force is 5 newtons. The distance from the hinge to the doorknob, R, is 0.72 meters. And the angle theta is 57 degrees, the angle between the distance vector and the force vector. We use the torque relationship. So the torque is equals to the distance from the pivot R times the applied force times the sine of the angle between them. And now we can substitute the values. So R is 0.72 meters, F is 5 newtons, and sine 57 degrees, and we get 3.019 Newton meters, which we round to 3 Newton meters based on the given data. This answer makes sense. The force is not huge, but it is applied fairly far from the hinge and at an angle that has a strong perpendicular component. So the door experiences a noticeable turning effect. The main takeaway from this video is that torque depends on force, distance from the pivot, and angle. To create a larger torque, you can push harder, push farther from the pivot, or push more nearly perpendicular to the lever arm.